Hi friend, welcome to A Water Connection, a space created to learn, connect, and multiply the power of a conversation to give visibility to the water industry. I'm Jess Borges, a passionate human who believes you should increase your water curiosity. Welcome to this new episode, episode 18. Today, we're joined by Professor Denis O'Carroll, who's going to help us learn and understand a little bit more about PFAS in our daily lives and in the water sector. Denis is the managing director of the Water Research Laboratory and a professor at the School of Civil and Environmental Engineering at the University of New South Wales. His career has been marked by his commitment to using engineering to address pressing challenges facing the environment, water quality, and in particular, looking at contaminants in water. With experience in using nanometals for site remediation and investigating the toxicity of nanoparticles released from commercial products, Denis has more recently been focusing on investigating the fate and mitigation of PFAS. Welcome to A Water Connection, Denis.
Thank you for having me. I appreciate it.
And I'm going to start with a very basic question, but I just want to make sure that all listeners are on the same page. Denis, what are PFAS?
They're a synthetic chemical, or a group of synthetic chemicals. There's over 14,000 PFAS as distinct chemicals that we've used widely in consumer products and in industrial applications for the last maybe 70 years. And they have exceptional properties. So yeah, we use them pervasively.
Okay. So where did these substances coming from? So you're talking about they came from some applications, or how were they created in the first place?
Well, I guess in chemical reactors. So we make them, let's say, for firefighting foams. And what we do is we use them to smother fires. So they have a foam. And when you have a fire, you don't want oxygen to get in to let's say if it's an oil fire and burn. So what the foam does is it gets in between the oil and the air, and it creates a barrier. And the PFAS parts of it, they're really, really strong chemicals, so they don't readily break apart. So in high temperature, or like in fires, they can effectively smother the fire but not break apart and put out the fire rapidly. So that's one reason why we use it. We would also use it sometimes in our cookware in the kitchens. We'd use it maybe, I'm not sure about this jacket. This jacket's relatively new, but in old rainproofing, we would use it so the water doesn't get through. Use it for stain resistance in carpets. In a wide number of applications.
Yeah, because it's basically applications where we need to kind of isolate something from another thing. So foam,
That's right.
like in the case of the fire, like the air and the fire, and like cookware and all of that. Why do they take so long to break down? You mentioned that just earlier. Why do they take so long?
Well, I think just by design, there's a carbon-fluorine bond. That's one of the strongest bonds that we have out there. So it really doesn't break apart. So carbon fluorine is sort of part inherent in the molecule. That's what defines PFAS. And we've designed them so they won't break down. And so that they don't, and they have exceptional properties because of that.
Yeah, okay, I understand. So what happens with those substances then after the product is used, or I don't know, if the cookware is put in landfill, or the piece of clothing is on landfill, or what happens after the actual main use of these substances or these articles that have these substances has passed?
Well, they persist. There's over 14,000 PFAS. The majority don't break down, or they might take hundreds of thousands of years to break down. Some of them do break down, but when they do break down, they typically break down to the ones that don't break down any further. And the ones that don't break down any further are the ones that are regulated it's by governments around the world. So that they persist and they get into our soils and our waters, and we do find them sort of pervasive in waters globally.
Yeah, that was something that piqued my attention, of course, because this is all around water. But in one of your more recent interviews or articles that I saw, you were mentioning that PFAS are also present in our own bloodstream, right?
That's right.
Which I imagine, is that through the water that we consume, or is that us using those products, or a little bit of everything? Or
Well, it's part of everything, but certainly, yeah, I'm not sure that in let's say for me, I'm wondering, it would certainly be in my blood, and I'm not sure that I would have had been exposed to too much PFAS in the water through my life, but certainly I would have been exposed to PFAS maybe in food wrapping, as an example, historically, maybe in clothing, but certainly drinking water with PFAS in it is another important way that you could get it into your body.
Yeah, and like yeah, my focus is not to get into the body, but like more like introducing it into how it end up in our water bodies, which is what we want to
Ah,
discuss. Like
yeah,
so how do PFAS actually end up in the body? So it happens that it like the substances are in the soil, and then effectively that moves into underground water, or
that's right.
yeah.
Yeah, or surface waters as well. We find them if we went, let's say, around Sydney where I live. If you went around and sampled water, sort of the storm waters around, you would certainly find PFAS at measurable concentrations. We've done it sort of on the North Shore of Sydney, and also in the eastern suburbs, sort of near the ocean. And there's PFAS at measurable concentrations.
Yeah, yeah, of course. You mentioned earlier, and I did have that as a question, so that's why I didn't go into before, that some of these substances are regulated. So can you give us a little bit of a glimpse of how that works? Like, which, not which substances are, because I know this is not maybe very specific, but like, how are these substances regulated in our drinking water or in water bodies?
Well, it depends where you live. In Australia, there are three PFAS that are regulated. In the European Union, it's the sum of all PFAS. So the sum could be all of 14,000 PFAS. And that's the same in Canada. Different ways of how they quantify that. And the US EPA also has very stringent regulations around a subset of maybe six or eight PFAS. So all jurisdictions around the world regulate them differently. So it's sort of hard to keep track of. Um, yeah,
Yeah, and I think you were mentioning in another article I saw that it changes all the time. Like the regulations are
that's right.
updating all the
Yeah.
time, so it's hard to keep up with those changes. Yeah.
And you're right. And it's also hard. Or I think regulators or water utilities are somewhat careful because they may say that water is safe to drink today, but if the regulation changes, but there's and it makes it the water sample is okay one day, but then it becomes more stringent the next day. Then of course they have to change what they're saying. So
Yeah.
it's a little bit confusing.
Yeah. It could be quite a dynamic space to work on. And now I see what people are so interested on it because it's something that is changing all the time, and of course has the potential impact in our lives and in our environment. Talking a little bit, what can we do with these PFAS? What techniques are currently used to clean PFAS that is found in water?
Well, there are a few ways that we can remove PFAS from water. We can activated carbon is commonly used for treating water, so that works well. Ion exchange resins as well work very well. We're working on sort of advanced methods. So those methods just they concentrate the PFAS. They don't break apart the PFAS, but they concentrate the PFAS on the activated carbon of the resin. We're working on techniques to break it apart. We could send the PFAS contaminated soils or activated carbon or resins to an incinerator, high temperature incinerator, and that would actually break apart the PFAS. But there's only a few of those around in Australia as an example. So that would be a very costly water way to treat water.
Yeah. Especially you may not have that on site if we're talking about drinking water treatment plants. They might not
That's right.
have the
Yeah. No,
infrastructure for
yeah.
that.
No.
Yeah. And then these resins, they work similar. So the activated carbon, I understand, is like a filter, and then the substances just get trapped there, and then they
Yeah.
is the resin working in a similar
Yeah.
way?
Yeah. In a similar way, there's at a very microscopic level, it works a little bit differently. But yes, big picture, yes, they work the exact same way.
Yeah, okay. That's quite interesting. So those would be kind of the techniques that are currently used for
Yeah. Yeah.
this.
Yeah.
Yeah,
Yeah.
okay. In reading a little bit about your career, I learned that, and you mentioned it as well, that you kind of are working in new techniques to do this, and you were part of the team in a recent Australian Research Council or ARC grant where you're developing a new technique for this. How is this approach different to what exists right now? And if you could just give us a glimpse of these new techniques that you're developing.
Well, what we're trying to do is combine activated carbon and some other techniques where electricity reduction technologies, put them together to trap the PFAS and then concentrate it and then degrade the PFAS that's on the surface. So we're hope we're still in the development stages, but we are making progress. Yeah, and able to break down some types of PFAS.
Yeah, okay. Would that have the potential to like, yeah, bypass that step of maybe incinerating the PFAS or
Absolutely. So our thought would be is that you could have it at a drinking water plant, or let's say at a contaminated site, and you have PFAS contaminated water coming in, and then coming out, you would have maybe I don't know, methane or something like that, and water, and it would be completely PFAS free,
yeah,
and
okay.
no toxic byproducts.
Yeah, that sounds very promising. And I know I've been involved in research, so I know things kind of are to be developed like step by step, and like
That's right.
starting in a lab, starting even numerically, and then scale it up a lot more in the future. So, what can you tell us of all the techniques that might be out there in other parts of the world? Like, I'm sure through your research, you have contact with people all over the world, and I'm sure there's a group of very smart people somewhere looking as well as you team into what to do with these substances.
Yeah, well, this you're absolutely right. It's a big focus because there's a lot of PFAS in our waters, unfortunately. So, colleagues who we work a little bit with at the University of Sydney, they're using plasma and sort of a plasma technology to break apart PFAS. Other people are using, and some of my colleagues at UNSW are using a microbiology to try to break apart the PFAS molecule. Other people are using, we're using advanced reduction technology. Some people are using advanced oxidation technologies as well, which is, sort of the flip of reduction. So this is a range of things that membrane filtration is a range of things that people are really working on to try to get it. There's no one solution that'll fit all of the different problems. So that's why it's good to have a different range of different technologies.
Okay, so different technologies would work different for different of those 14,000 substances that are out there. Is that how?
Yeah, well, yes, and also the PFAS isn't the only thing that'll be in water. There's going to be something out there, there could be different pH. There could be, let's say, natural organic matter. You don't quite know. Water hardness is a big deal. So all that will impact how each of the different technologies work. So while at one location, one technology may work great because of, let's say, water hardness or pH or something like that, it may not work well somewhere else.
Yeah, okay, that's very interesting because we had in another episode we were talking with Sally Williamson. She works for Sydney Water, and she was explaining us how water treatment works. Right, that before PFAS, like just the
Yeah.
basics of it, and she was saying that one of the things that is quite interesting is that it's dynamic. Some of these things are changing all the time. So it's very interesting that now that we add the layer of these contaminants which are present and we really need to get our heads around it, the techniques to do that also are going to depend on the conditions of the water. So you almost would need to we almost need a technology that is as flexible as the inputs that we're getting. So it's quite interesting to learn that. Um, I would like to ask, like, what's your take on the interaction between you being in research with the water utilities? In your case, if you're based in Sydney, with Sydney Water or other New South Wales utilities, to test some of these or to get their insights into your research. What's your experience with that?
Well, we absolutely talk to the utilities and get their feedback and input because oftentimes when we start developing a technology, we use very ideal conditions, and as we want to move it towards, let's say, field implementation, we need to get an understanding of what are the other considerations, what might also be in the water, what are in terms of a plant, what else could be there, in terms of the plant operators. They need you want something that's very, very easy to use. So all those considerations, certainly we would absolutely be talking to them on a regular basis, and also what their needs are because there's emerging challenges as well. So we often want to get a sense of that as well.
Yeah, and I think water utilities, in my opinion, are getting a little bit more around, like using a lot of innovation. So they would be a little bit more open in many places to explore new things and new technologies that could help with this particular problem. Which, if they have like an established solution, that's fine. But if they still have to get rid of these filters or these carbonated active carbon and all of this, then is certainly an interaction that needs to happen there. I had another question here, which is related. What do you think is the role of water utilities or the water professionals that might not be directly related there with the operation of the plant to support the advancement of these techniques?
Sorry, water utilities. What's their role?
Or people that might not work, because our listeners might not work, all of them, in water utilities, and we're learning about
Okay.
this. But what else could we do from roles that are a little bit different?
Well, sure. I think is definitely. I think we always have to have a dialogue in the larger water community to find out what are the challenges and sort of figure out what are the different possibilities in terms of dealing with the problem, and then also putting it in perspective as well. Sometimes, uh, sort of sometimes in the media, it what's reported causes a lot of concern to the public, and we also have to have some sensitivities and making sure that the messaging is right, such that we do acknowledge that there are issues, but also not get people afraid such that they don't drink water.
Oh, absolutely. I think that you touch on a very important issue that I have talked to many people, and is how can we as water professionals help the community to understand value of water, how important it is, but also around these concepts that is not, yeah, sometimes the angles that get to the public are a little bit different to not a reality, but they just take on a different angle, and we need to be there to support people and, like,
Yeah,
let them know that we actually water utilities are regulated to do these things that are on top of their game, and that there is people in research working to develop what the next steps will be. So I think that's, yeah, it's an excellent point that you make there. There are a couple of questions that I always ask to my guest, and you touched a little bit on this before. But what do you think is the biggest challenge that the water sector is facing at the moment?
oh, that's a great question. I think, well, obviously, contaminants, emerging contaminants are a really big deal, and sort of trying to anticipate where the regulatory environment's going. Because if if you install a treatment process to treat a contaminant, but then the regulations change in a couple of years, then that costs a lot of money. So it's easier it's easier to plan for it in advance. I think carbon emissions are a big deal as well, and lowering the carbon footprint of our utilities, be it water or wastewater as well, certainly is something that is we're acutely aware of, and sort of the a circular economy, and try to minimize our sort of environmental footprint as well.
Absolutely, yeah. We have tried to touch on all of these topics before with
Yeah,
other guests, and I think what you mentioned about, like, the regulatory dynamic, which we have talked, but also infrastructure projects take a while to, like, from, oh, we need this, to here's the day that they are functioning. So maybe we need to think a little bit more on how do we develop projects in infrastructure but keep them flexible. So if at any point in time, like, there's a new regulation, or there's a new technology that is promising or has been in the pipeline for it, we can implement it a little bit quicker. Otherwise we're kind of chasing the regulation all the time. And yeah.
yeah, that becomes challenging for sure.
Yeah. Dennis, what would be your message to young water professionals who might be listening to you right now, or students that might be listening to you right now? What would be your message for them?
Well, it's an exciting field, and things are continually changing. So it's an opportunity to learn and sort of lifelong learning and really help the community, help society in terms of drinking. Obviously safe water is what I do. Um, yeah, I'm quite passionate about it.
Yes, I can see that. And related to that, what do you work in water? What do you work in the water sector?
Where do I work?
Why? Yeah.
Why? Oh, why? Oh, yeah, I guess to have an impact. So, so I go to work every day, and it's something I think about quite often, is that I have a positive impact to society, to help the betterment of humankind. Yeah, and really, I do, helping first world countries, but also do try to also help, sort of developing countries as well. Well, because our water quality is typically in first world countries is quite good, and we're talking about PFAS this episode, but they have likely more pressing water quality concerns.
Yeah, absolutely. I was just when you started mentioning third world countries, I was like, oh, I want to know a little bit more. um, do third world countries have access to these techniques to deal with PFAS, or is it more like a step process? Like, you get rid of the really things that you need to get rid of to make water drinkable, or because they might have help or support from first world countries, they're able to bypass that step and kind of have something for PFAS as well. What's your take on that?
Well, certainly they would have access to these technologies, activated carbon, for example, but it can be expensive that. But something like um, they might some of the water sources might have microbial contamination, as an example, which will is acute, and it will kill you right away. You get diarrhea, and that's a much more pressing concern, I would suggest, than PFAS, which it takes a long time to act.
Yeah, yeah, that's right. Like it's all about like having equity and like for us to be able to provide the same minimum service, and then kind of going to doing the next step.
Yeah.
But yeah. Thank you very much, Dennis, for your time. This was an amazing introduction to PFAS. I know I ask like the very basic questions, but it's to just make sure that we give a little bit of an introduction to everyone listen to us today. So yeah, thank you for all your insights and for all your knowledge today.
My pleasure. I really appreciate it. Thanks a lot.
We
Goodbye.
might do we might do more episodes in the future with PFAS, diving into different topics. But thank you very much for being today with us, and thank you, my friend, for listening to this episode of our Water Connection. I hope you enjoyed this 101 class of PFAS with Professor Denis Carroll. I had a lot of fun asking a lot of really basic questions in an area that I'm not that familiar. Please follow us on LinkedIn as a Water Connection to hear all the updates and new episodes coming. You can also listen to us on Spotify, Apple Podcasts, or your favorite podcast platform. We're probably there. And if you want to watch us, we're on YouTube. Help us grow this project by sharing this episode with colleagues, friends, and family. And yeah, help everyone increase their water curiosity. Help me in this mission. Until next time.